There have been a number of reports from agencies like NASA and SpaceX that they have been on the receiving end of an unknown signal that seems to be coming from the center of our Milky Way. However, they have been keeping it a secret from us people. But what is this signal? Why is it being kept a secret? Is it something to worry about? Continue watching the video till the end to know more. Hey everyone, and welcome back to yet another video from our channel. We hope you guys are doing extremely well. In this video, we will be talking about this unknown signal that is reported to be coming from the middle of the Milky Way. We will be diving deep into every aspect of this news, so if you are new to this channel, then make sure to hit the subscribe button. Now, without any further ado, let's hop right into the video. For 13 years, astronomers believed themselves to be lucky. They have been studying fast radio bursts, FRBs, from outside our galaxy. And then they became luckier still. On April 28, 2020, two ground-based radio telescopes detected an intense pulse of radio waves within the Milky Way. It was the first time an FRB had ever been detected within our galaxy, and despite only lasting a mere millisecond, it was almost impossible to miss. Located just 30,000 light-years away from Earth, the FRB was picked up by the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and the Survey for Transient Astronomical Radio Emission 2, STARE-2. CHIME wasn't even looking in the right direction, and we still saw it loud and clear in our peripheral vision, said Kiyoshi Masui, assistant professor of physics at the Massachusetts Institute of Technology. STARE-2 also saw it, and it's only a set of a few radio antennae literally made out of cake pans. Ideally, astronomers would discover an object and focus one or more different telescopes on it. But the ephemeral nature of these bursts removes any such opportunity. Indeed, despite being 100 million times more powerful than the Sun, releasing as much energy in a few thousandths of a second as the Sun in 100 years, they've been and gone in the blink of an eye. We also know that most of them come from billions of light-years away. But while dozens of models have been proposed to explain the origins of FRBs, with progenitors ranging from neutron stars to white dwarfs to cosmic strings, they've remained something of a mystery. An enormous amount of human time and energy has been devoted to working out exactly what they could be. Having discovered an FRB in the Milky Way, astronomers have been firming up their theories. Well, we know that they come from very small sources, no more than a few hundred kilometers in size, Masui said, and the most likely sources are neutron stars since they are both very small and very energetic. Some nifty cosmic detective work has been carried out, involving the data of other telescopes monitoring the same patch of sky as we're about to see. Observational evidence is now suggesting that the origin of FRBs is very likely a magnetar, a type of young neutron star born from the embers of supernovas with a magnetic field 5,000 trillion times more powerful than Earth's, thereby making them the universe's most powerful magnets. But how has this conclusion been drawn? To explain, we must consider the work that has gone into studying FRBs in relation to magnetars, which are known to emit high-energy electromagnetic radiation, notably gamma rays and X-rays. Both of these erupt in short-lived flares, and there has been speculation that radio waves could be emitted in such a process that would pinpoint magnetars as the source for FRBs. When this latest FRB was discovered in our galaxy, known by astronomers as FRB 200,428, it was found to have originated in the constellation of Vulpecula, which just so happens to be where the galactic magnetar SGR 1935 plus 2154 is located. It was also accompanied by a burst of X-rays that further excited astronomers. The first detection of X-rays from that sky region came the day before CHIME and STARE-2 discovered FRB 200,428. The Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope detected multiple X-ray and gamma ray bursts coming from SGR 1935 plus 2154, which was known to exhibit transient radio pulsations. Other telescopes were also found to have observed an X-ray burst from SGR 1935 plus 2154, crucially at the same time as the fast radio burst. These included the CONUS wind detector on board NASA's GGS-1 spacecraft and the European Space Agency's Integral Space Telescope, both picking up an X-ray burst at the moment CHIME and STARE-2 recorded the FRB. STARE-2's trio of radio detectors were cobbled together by a student using household items. What this means is that the FRB came from the direction of a known magnetar within our galaxy, and the radio burst happened at exactly the same time as an X-ray burst coming from the same magnetar, Masui said. It's a clue as to how magnetars produce FRBs, but the community is still trying to work out what it all means. What has become clear is that FRB 200,428 is the first observed fast radio burst to send out emissions other than radio waves, and scientists have benefited hugely from having discovered an FRB so close to home. The detection of the X-ray burst at the same time as the radio burst confirmed a magnetar as the origin, and it's the evidence astronomers have been looking for. The discovery of an FRB in our galactic neighborhood is significant because the proximity makes it a lot easier to follow up the source with telescopes observing at other wavelengths, Chawla said. None of the FRBs ever discovered have been known to emit at any other wavelengths, and this is the first detection of an FRB at a different wavelength. These observations can probe the source environment in greater detail, providing clues about the origin of FRBs. CHIME in particular has proven to be an essential tool. Based at the Dominion Radio Astrophysical Observatory in Canada, it's a novel radio telescope with no moving parts, and it has a high mapping speed thanks to its 200 square degree field of view and broad frequency range of between 400 MHz and 800 MHz. Most radio telescopes aren't able to pinpoint the location of an FRB well enough to associate it with a known object. Those that can localize FRBs with great precision usually look at small patches of sky and can only observe a patch about the size of the full moon. They are not able to monitor several known magnetars at once, Chawla said. CHIME, however, observes an area about 500 times larger, and it can therefore monitor all magnetars located in the northern sky every day, allowing us to detect a burst as rare as this one. It combines its localization capabilities with the large sky area, and that has allowed us to both detect this burst and associate it with a known object. In January 2022, scientists at McGill University revealed the development of a new system for sharing the vast amounts of data generated by CHIME. Making use of a standardized language for reporting astronomical events called the Virtual Observatory Event, astronomers can send information about FRBs, several of which happen each day, to observatories around the globe in real time. The idea is that astronomers will be able to quickly turn their attention to the location of the FRB source. The enormous volume of data that CHIME/FRB generates and the large number of new FRBs that it detects each day is like a gold mine for a community that is eager to point every kind of telescope that exists at the next FRB, says Andrew Zwaniga, lead developer of the CHIME FRB VO event service and a research assistant in the Department of Physics at McGill University. The burst we saw was still less energetic than most extragalactic FRBs, so we cannot say for sure whether magnetars can explain all FRBs. Chawla said of a burst that was 1,000th of the energy of any equivalent found outside the Milky Way. So what are astronomers learning? Well, it may be the case that weaker bursts are more prevalent, and that it's simply a matter of this one being close enough to detect. But when it comes to pinning the source of FRBs on magnetars, astronomers need to remember that they come in two guises: those that have repeating signals, which means they frequently generate the outbursts over and over again, and others that, like FRB 200,428, generate more infrequently. It could be the case that infrequent FRBs are caused by magnetars and the frequent ones are caused by different phenomena. On the flip side, it could also mean that two types of magnetars may exist, causing the two different types of fast radio bursts, or even that the brightest FRBs are caused by objects other than magnetars. Only further research will shed light on the answer, since all we can say for sure is that at least some fraction of FRBs come from magnetars. It's been suspected for some time that magnetars might be the sources of FRBs, but this confirms it for at least some fraction of them, since we've seen it happen once, Masui said. But we still don't know how magnetars create them. We know the what, and next is the how. How do magnetars do it? As such, it remains important to discover what powers an FRB to emit such energy. Perhaps electrons interacting with magnetic fields creating an engine of sorts. We would be interested in determining how extreme the properties of these magnetars need to be to allow a burst from it to be seen across the universe, Chawla said. But the most interesting application of FRBs would be to use them as cosmological probes to study the distributions of electrons and magnetic fields in the universe with unprecedented detail. And that's all for today. Did we miss out on anything? Do you have any other insights on this news? Did you enjoy watching the video? Let us know your thoughts in the comments section down below. Well, that brings us to the end of this video. We hope you have enjoyed watching the video. Please like the video if you have not already and make sure to hit the subscribe button. Don't forget to press the bell icon to never miss another update from our channel. With that being said, let's meet in another one of these videos. Until then, see ya!